Hey folks, we're back and we are looking at section 6.4 for elementary statistics, which is the central limit theorem. So now the central limit theorem tells us that for a population with any distribution, the distribution of sample means approaches a normal distribution as the sample size increases. Now you're probably saying, what? No. So we're going to look at a couple of examples to kind of show you exactly what's happening. So the procedures in this section form the foundations for estimating population parameters and hypothesis testing, which will be seen in later chapters. Unfortunately, we don't get to hypothesis testing, but we will be doing some estimating of population parameters in the next chapter. All right, so we're going to look at three cases. So we have a normal, we have a uniform, and we have a U-shaped. Now, the first thing you have to understand is that we're looking at a population that has that distribution. So if we looked at this first case where you have a normal population, a normally distributed population, if you were to take a sample from that, you would kind of expect that the distribution from that sample would also be normally distributed. And if you were to take 10 samples and then take a look at its distribution, it should also be normally distributed. If n was 50, again, you still have that same type of distribution. Now, the one thing you do notice is that it does get skinnier and taller. So that's something that we'll address a little bit later on. But the big thing to keep in mind is that because it always has that normal distribution shape, we can use our tables that we've used in the previous sections. Now, the big question is what happens when the population is not normally distributed? So in the case of a uniform, you can see if you take a single sample, we're going to have that uniform distribution look. But as you take more and more samples, it starts to form a normal distribution. And once you can see at n equals 50, you get that normal distribution shape. Again, skinnier and taller though. And it doesn't matter what that original distribution looks like. Eventually, as n gets large enough, it's going to form that normal distribution shape. So that's the conclusion we can make here. As the sample size increases, as n gets large enough, the distributions of sample means approaches a normal distribution. Now, this terminology of sample means is explained more in 6.3, but it's not absolutely critical to understanding how this section works. So that's why we skip over it. All right. So if you want to know more about this language of sample means, that's talked in the previous section. We'll kind of hint to it here and there, but overall, we're not going to dive deep into that terminology, that description. So what's the takeaway from this? Although we can see the distributions above each approach a normal distribution, question, what is the minimum number of samples for this to occur? So like I said, when n was 1, obviously we don't have a normal distribution. At n equals 10, it's sort of looking normal. N equals 50, definitely we have that normal distribution. So what's that happy number that we can use to say, okay, now we know it's normally distributed once we get to this value of n? And the answer is it depends on the distribution of the original population. And for the reasons we just set up above, that's going to be important. If it's normal to start with, it's always going to be normal. It doesn't matter what n is. It's only when n is not normal that we need that specific cutoff of what's that value of n where it's finally going to be normal. So let's take a look at those two cases. So we have our given information. We're going to have a population with a mean and a standard deviation. And we have a simple random sample of the same size n selected from the population. So again, simple random. We like simple and random. So we're pulling a sample from that population. So the first case is that the original population is normally distributed. And what we just set up above is the conclusion they draw here. For any sample size of sample of size n, the distribution is a normal distribution and the central limit theorem can be applied. Now again, the notation that they're using here of X bar is not critical to understanding this topic, so don't get lost in that part of it. The big thing to take away from this is that when you have a normal distribution, there's no restriction on what n can be. And as a result, the mean is one thing that we don't have to worry about because it doesn't change. So for the sample or in general, it's always the same thing. But the standard deviation will change based on what the value of n is. So, and we're going to see this in detail with some specific examples, so don't freak out yet. So the standard deviation is going to change a little bit. And as long as we remember to divide it by the square root of n when we have an n, then we're going to be okay. So that's the first case. So it doesn't matter what n is. That's the takeaway. When the original population is normally distributed, any n will work, and we're fine. So what happens when it's not normally distributed? So in that case, when it's not normally distributed, we have to have a large enough n. And the only time it's large enough is when n is greater than 30. So that's the important cutoff for this. Once you get beyond that threshold, then the central limit theorem applies and you have those same conclusions. The mean doesn't change and the standard deviation changes by whatever the value of n is. So, and then the third case, which really isn't a case because we can't do anything with it, is when n is less than or equal to 30. And when it's less than or equal to 30, we can't even do anything. We cannot approximate it with the normal distribution, and we cannot apply the central limit theorem. So we're busted. So hopefully we only have cases that is one of the first two. Now to kind of reframe this into an example, let's take a look at example 1, and then we'll stop the video and then we'll see how to apply it in the next one. So if selecting samples of size n from the original population with a known mean and standard deviation, what must be true about the original population in order to assume that the central limit theorem applies given the following sample sizes? So when n is equal to 2. So the first conclusion you should make is that n is small. If n is small and we want to be able to assume that that sample forms a bell-shaped curve, what do we have to know about that original population? So essentially, which case are we looking at? And the answer is the first case. Because n is small and we want to have a normal distribution, we're going to have to assume that the original population was normally distributed. So that's your answer. Since n is small, and n is basically less than or equal to 30, then the original population must be normally distributed. Because then it doesn't matter what n is. N can be small, n can be big, and we always will have a normal distribution for that sample. But in the second case, when n is 31, now n is large. It beats that threshold of 30. So do we have to have in our original population be normally distributed, or could it have any distribution? The answer is it could have any distribution. We're not restricted anymore. Once n is large enough, the original population could be distributed like a squiggly line, and it would still be able to be applied, the central limit theorem. So that's what we would write for this answer. So since n is large, and by large I mean n is greater than 30, then the original population can have any distribution. So that's what we can refer back to the original information. We need to know if we can use that central limit theorem, but it depends on n, and it depends on what that original population has for distribution. A lot to absorb in this, I know. We're going to see how it applies in the next video and the takeaway. The takeaway is much, much easier than trying to frame all this in your mind, I know. So just try to bear with me and watch that next video. See you in a minute.